welcome back, everybody. So I let you go back to your seats. All right. So we are going to start with the questions that were pending right before the break, and we can start with you. Go ahead.
Yeah, I have a follow-on question from Max's. You said that row ID could sort of depict a semantic meaning, but that would imply that because these are binary representations, the row ID to be a unique value. For example, social security might work, but a name wouldn't, right?
So yes, the row IDs must be unique. You cannot have two rows with the same row ID. What I mean with the fact that they can have a semantic meaning is that since the user can freely pick the row IDs that they want, they can decide that these row IDs encode specific things, right? But HBase will not know. HBase will just see the sequences of bytes, right? Did that answer your question? Yeah, awesome. Any other questions? I don't see any other raised hands. On Zoom, I also don't see anything on Zoom. All right, so I'll continue, but again, you can at any time interrupt, even for previous material. It doesn't have to be exactly what I'm talking at the moment at which you ask the question. So the last one, as one of you correctly said, is delete. We can also say that we want to delete a specific row. It can even be a specific parts of the rows, like specific column family and so on. So you see the random access in there because again, you can read single values, you can put single values, you can also do multiple at the same time, but it's really very fine grains because we are looking at, it can be 10 megabytes, it can even be smaller than that, right? If these are not even JSON or XML documents, that just simple strings or simple dates. So it's really random access. And at the same time, you can run data analytics over an entire table of a petabyte. As we will see, we can use Spark and MapReduce later. So it's a little bit like a Swiss Army knife, right? It can do a lot of things, random access reads, random access writes, scanning over intervals of row IDs, storing XML, storing JSON, huge sparse tables with many columns created on the fly, and so on and so on. I wanted to say a word also based on some discussions during the break. Again, do not forget that the row ID is really special. It's not a column like the others. It really is a first-class citizen in the column store. So there's really the row ID, which is just that one, and then you have the column families. In a relational database system, you have more flexibility. You could designate a primary key as any column. You can even have compound columns as a primary key in PostgreSQL. Here you can't. It has to be really just this one row ID. There's other systems like Cassandra. Who heard of Cassandra? It's Facebook's or Meta's version of a white column store. In Cassandra, I think you can have multiple columns for the row ID. But this one is really special. And now I understand also why you asked about ranges of values, because it looks like values like any other, right? So if you have ranges here, why don't you have ranges there? And here, the notion that you need to understand is that of primary index and secondary index, right? We'll see in MongoDB especially. In a database system, you usually get an index for free on the primary key. It's very common that when you have a primary key, the database also has an index or has some efficient way of retrieving the values for a given key. If you want to have the same functionality for other columns that are not the primary key, that's called the secondary index. And a secondary index, typically, you have to ask for it. The database system is not going to do it for you. There are exceptions. There are smart database systems that also figure out secondary indices based on your pattern in querying. But typically, the secondary indices are yours to build, while the system supports the primary index. And again, while in PostgreSQL or MongoDB, you can very simply require a secondary index to be built, and it takes care of it. In HBase, that doesn't exist. You cannot ask HBase to build a secondary index. You would have to do it yourself or use another technology that would build that index. All right, who is with me? Okay. And another thing I wanted to say that might give you a different angle, you could view HBase as a two-dimensional version of Dynamo that has range querying of keys. Who sees that? Okay, so two-dimensional because you can see it as a two-dimensional grid, right? In object storage or key value storage, you have one dimension, that's the key, right? That's all. Here you have 2 dimensions. It's a grid that you can build with values and XML documents, JSON documents, and so on. So it's two-dimensional. And with range queries, because you don't have any ranges in key value storage, but in HBase, you can have ranges of keys. All right. Okay, so we are done for this. Some terminology, because that at that point, you might have some confusion between what we call what. A key value model is just a high-level logical abstraction of whenever you have keys and values. For example, here we have an implicit key value model in the sense that the row ID is the key and the row is the value. You also have a key value model in S3, where the key is the bucket ID and the object ID, and the value is up to 5 terabytes. You have an implicit key value model in Azure Blob Storage, where the key is made of 3 components, right? The accounts, the partition, and then the specific blob. You have a key value model in JSON at the level of one object, right? In JSON, you have keys and values within an object, right? You have a key value model in the attributes in an XML element, right? So you have the key value models, it's absolutely everywhere. It's whenever you have some keys associated with values, can be physical, can be logical, it doesn't matter. So key value model is something very general. But if you say key value store, then you're very specifically referring to things like Dynamo with the ring and the hashes and distributed hash tables and so on. So key value storage is something very specific. I'm not sure why it went back. Maybe I clicked on my, yeah. So that's the key value model. It's whenever you have keys and values. You even have it in HDFS with the block IDs that are keys and the blocks that are values, right? So when I'm saying everywhere, it's really everywhere. Okay, then we have column-oriented storage. That's what I told you was invented before white column stores. It's an alternate physical level for relational database systems, right? That made it's efficient to specifically read only data that you're interested in or to create new columns on the fly. We just physically on the hard drive store it column by column instead of row by row. That's called column storage or column-oriented storage. And white column storage, what we are doing now, is really family by family, right? There can be millions of columns here, very sparse, a lot of values that are not even here. And when I'm saying they're not even here, I don't even mean null. I mean they are really not here. It's just sparse. There is nothing stored physically if a value is missing. And again, for the big picture, I already mentioned Bigtable as the proprietary version of Google. It's no longer used now. It's another system that we'll look at the very end that is even larger. Because yes, a few petabytes of data is so 2010s. Now we have to have exabytes of data, but I'll tell you later. Apache HBase, that's the one we're looking at, the open source version. Cassandra is this other system. It has a different design, but still on the high level, it's similar to HBase. Okay, so now you know you can put them together in your mind. These are white column stores. Okay, and now we get to the scary parts, the physical level. I would almost need a music that is scary for that moment. Who is ready for the physical level? All right, you can interrupt me at any time to get into it. If I don't know, I don't know, but I will try to do it in such a way that everybody is following. So the cliffhanger question for this is, I just told you that we have a system that gives you random access reads and writes. And I also told you it's implemented on top of HDFS. And HDFS doesn't have low latency and doesn't support random access reads or writes. Who sees that there's a mystery in here? Right? How do we manage to do it on top of HDFS that doesn't have random access? And you will see, I will show you how it's done. And what we'll discover along the way is the notion of batch processing. That's the second. I already told you about parallelism between capacity and throughput. And between throughput and latency, that's batch processing. So we'll see it for the first time in action right here. So let's go. The physical level, that's what's hidden, what the user doesn't see, the user of HBase. You remember that when we organize things in S3, we partition by buckets, remember? So we organize the data in these bigger zones. This is something that we'll do a lot, as we will see when we have Spark and MapReduce. When we want to parallelize the data, or when we want to spread it over machines in a cluster, we need to just divide the data into chunks. Do you remember what they would be called in HDFS, these partitions? A file is partitioned in? Oh, I know you know. Who knows? Okay, many raise hands. Can you say it at the same time? A file is partitioned in? Blocks, exactly. Been following. Blocks, yes, absolutely. And here we do the same thing. We will partition the rows, and the name we have for this partition is region. So a region is an interval of rows, a range of row IDs. Because we are geeks and we are computer scientists and we like beautiful design, the way we specify a range is with minimum inclusive and maximum exclusive. Why? Because the maximum exclusive here is the minimum inclusive of the next region, right? So then we just reuse the same row IDs for the boundaries. All right, so this here is called a region. There's another region here, there's another region here, but we partition the row ID space in regions. And again, it's sorted. So the region is a contiguous interval of row IDs between a minimum and a maximum. Right, so that's the first thing. At that point, it's a logical partitioning because we are not done here. We also partition it in column families. So it's like a wedding cake. Literally, I cut it vertically, I cut it horizontally. And the one thing that I'm going to store together is a specific region intersected with a specific column family. All of the values that are in there, we'll store them together on the cluster. So imagine that if this is a region and this is a region, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 zones that we store together, partitions. Who is with me? Right, and I have to yet show you how it is stored together. But this is the first thinking. We just cut it into smaller pieces, and each one of these pieces is more manageable. In particular, it can be handled by a single machine. What about the architecture? Who knows Zinor 4.1? Right, so that's pretty much the same procedure. We have name nodes and data nodes, and for HDFS, and we are also going to have that same centralized architecture for HBase. It looks like this. We just changed the names. Now we have an HMaster and a region server, and that's pretty much it, right? There's nothing new. So now you just need to learn HMaster, region server. Do you remember that I told you, even though we say the name node or the data nodes, having a machine in mind, I told you if you want to be precise, it's a process that runs on a machine. So you have a name node process running on the machine on the top, and you have a data node process running on each machine below. Now what you need to picture is that on these same machines, in addition to the name node process, you also have an HMaster process on the same machine. And on everyone on the other machines, you have a data node process and a region server process. Also on the same machine, there's just two processes. Just like on your laptop, you might have a browser open and then maybe your email client software, right? So we just have these processes running on the same machines. The fact that they are on the same machines is important because this is how it's going to be efficient. Because we'll have less data that needs to be sent over the network if we can just read it from the same machine. Who is with me? Right. So we have this centralized architecture once again with the HMaster and the region servers. So we'll start with the HMaster. The HMaster, that's not going to be very surprising, is responsible for the metadata or DDL operation. Who remembers what DDL means? Yes? Data definition language, exactly, as opposed to data manipulation language. So DDL is everything about the schema. So whenever you want to create a new table, you want to create a new column family, you want to, well, that's pretty much it, because some of the things of HDFS, the analogy stops here. You remember in HDFS, you can create a directory, delete a directory, create a file, you need to go through the name node, and then you connect to the data nodes for the blocks, right? And so for the very high level operations on the table, you also go to the HMaster. We'll see that the client has a bit more autonomy than in HDFS. The client can also directly speak to the region servers, but we'll see that. So far, so good? Right, so that's in common with HDFS. For the high-level stuff, you speak to the coordinator node in the centralized architecture, and then the data itself resides on the other machines. So create a table, delete a table. Now, what does the HMaster do? It decides which region corresponds to which region servers. So every region is assigned to one region server. That's an example. Remember that the regions are partitions of the row IDs. So it's intervals. There's a region 1, region 2, region 3, 4, 5, 6, 7 regions. And these regions are assigned to these region servers. So there's 4 region servers in that example. In practice, it could be thousands. 4 region servers. These ones have 2 regions assigned, and this one has 1 region assigned. Who is with me? Right. Now you might be wondering, well, that's surprising because for blocks in HDFS, we stored the blocks in 3 different data nodes, right? 3 replicas. And here I'm telling you, we only assign the region to 1 single region server, right? So who is wondering, why are we not redundant here, right? So several of you. Well, what you need to understand is that when I'm saying the region is assigned to a region server, I'm not saying that the region server stores the data. The data is stored where? In H? Yeah. Exactly in the data nodes of HDFS. So the data is replicated 3 times because it's all in HDFS blocks, right? So the data is on HDFS. You don't have any problem with losing any data. So the only thing we are saying is that when we say the green region is assigned to that region server, all that means is that this region server has the responsibility for that region, right? But it still stores it on HDFS. So that means that if a client needs to read the data in there, then the client has to contact this region server right there. For whom is that clear? For whom is that not clear? Don't see any raised hand. Okay, you know you can interrupt me at any time again, right? So we have the wedding cake. We partition horizontally and vertically, and every region, horizontal partition, is assigned to a region server. So it means that when a region server is responsible for a region, it means it's responsible for all the column families in that region, right? So they're still together on the same machine, but we'll see when we store them on HDFS, we'll do it column family by column family. Yes?
But isn't then the regions of a single point of failure for for the client itself, because that is the only point that it can go to while trying to access a particular region?
Yes, you have to think of the single points of failures. In that case, you first need to realize that as far as the data is concerned, it's stored on HDFS, so it's not lost, right? Imagine a region server fails. It's also a data node, so you might use a few blocks, but you're going to have replicas at other places. So what happens if a region server fails is you just reassign the responsibility of the regions to other region servers. They just read the data again from HDFS, right? Does it make sense?
Yeah, but like one more thing is like while in an HDFS, isn't it like whichever sort of data node which stores the data is like closest to the client, that is the one that answers for the particular data. While in here, we have a sort of a latency issue because there is a particular region server being assigned.
So yes, you are correct that if there is a crash and you reassign to another region server, that might have a bit more latency because that region server might have to request blocks that are not on it. Right, so it involves some communication over the network. So it does mean that indeed, when you hand over to another region server, it might be a bit slower reading from disk. But we'll see that there's all kinds of optimizations on top, like caches and all kinds of things that mitigate that a little bit. So it's basically a price we pay that if a region server fails, it might slightly become slower for a while. But then as you continue to write, then again, you'll have locality. Right? Does it make sense? Yeah. Thank you. That's good thinking, like the having to think of single points of failures, like the fact that there's only one region server, you have to ask yourself the question. So great. Yes, over there, another question. Now you're being very cautious, Dalia. Very, very nice. Go ahead.
In the case of failure, for example, like we cannot access a certain region server. How do we recover? Like, how does the HMaster recover where the data is assigned? Because
you mean the information of what is where?
Yeah.
Yeah. So the information of what is where, and here it's a difference with HDFS. It's actually not on the HMaster. There's actually a special place. It's a special table actually that looks like another table in HBase. That is the root table, and that root table looks like actually this. The root table also looks like this. And it's basically a list of regions and where they are on the network. The logic of that is actually done with a distributed system. I think it's Zookeeper, which we don't cover in that lecture, but there is a distributed system that allows the nodes to know where that root table is. And whenever somebody needs to know where a region is or who is responsible for the region, they would look at the root table in there. And that's a different system that is besides or as a helper to HBase that ensures that this root table is somewhere and available. And knowing where the root table is done with a distributed protocol that is on a lower level.
So when you set up the whole system, is it the HMaster that provides to the region server where the actual data is, or does the region server connect to the root table?
In terms of the exact protocols, so that I would need to check if there's also the notion of heartbeats. I suspect there's something like this, right? That the region servers can register to the HMaster. I could investigate this a little bit and tell you more about the physical architecture, right? By the way, if you want to connect it with HDFS, the fact that we have some physical distributed system like peer-to-peer to decide on where the root table is and how everybody knows, that's a bit similar to how in HDFS you have this Chrome journal manager to synchronize between the standby data nodes, right? That keeps track of where the standby data nodes are and to elect a new name node. Did I say standby data node, standby name nodes, and to elect a new name node from the standby name nodes. That's also a distributed system. And there's courses at ETH, I think Roger Vattenhofer and maybe others teach these things. It's you can do a whole semester course to describe all of these protocols, right? Okay. Did I answer your question? Right. And if you could take note of this, I'll try to come back to you on some more details about any heartbeats between the region server and the HMaster. Don't see any other raised hands on Zoom. Also not. No, not on Zoom. All right. So, yep, we have the region assigned to the region servers. And you already asked the question, but basically, if at some point you want to reassign, that's entirely possible. So here's a concrete example. Imagine that a user keeps inserting row IDs always at the same place. So it's called the hotspot, right? You have a local place in the row ID interval where suddenly a lot of data comes in and a region becomes very big. Then what can be done? It's spontaneously done by the region servers. They just split the region, right? So for example, if the blue region becomes big, you can split it into a yellow region and a blue region. they still stay handled by the same region server, we just split it. So it means in the root table, we would also enter the information that now it's 2 regions instead of just 1. But now this machine has 3, so you could at some point also do some load balancing and just decide, even if it didn't crash, you can reassign the region to some other machine, right? Again, that might imply some latency because the data might no longer be local when you do that, but you can, in principle, just reassign because the data is on HDFS and it's accessible from everywhere. Who is with me? Right? Okay, so this is how we decide who is responsible for what, which region server is responsible for what region. And if there is a crash, like this region server crashes, the second one, you just reassign the 2 regions to other region servers and the system just continues to work. Okay? So we are done with the HMaster. Now we go to the region servers. So that's a repetition of what I said. We partition like a wedding cake, horizontal, vertical. So we have the horizontal partition into, what is it called? Regions, yes, region 1, region 2. And then we also partition in families. Now, again, to repeat things, all of the column families within the same region, that gives us 3 stores here. They're all handled by the same region server. And these 3 are also handled by the same region server. I'm going to call them stores. I'm not sure if it's an official name, but we need to call them something. So I'm just going to call it store. So in a store, what do we have if I zoom in? It's a specific region, so it's a range of row IDs that are sorted, and it's a specific column family. So that's a bit simpler than the big table, right? It just has a single column family, so the same one, and then just different column names. And the name we have for a single value here is a cell. It's a cell that corresponds to this row ID and that corresponds to this column name. So what we need to do is store the cells on the disk, on HDFS, store every cell together with its coordinates. Which row ID was that and which column name was that? All right, who is still with me? Okay, I'm checking periodically because as I said, it's the most difficult one. So making sure that nobody gets lost. The next thing to know is that this store, this set of cells, is going to be stored physically on HDFS, and who says storing physically on HDFS implies as files, because what you store on HDFS, they are files. So you need to store files. We have a name for these files. These are called HFiles, very original, right? So HBase file, HFile. So this logical partition, its logical view with the rows and columns is physically stored in one or more HFiles that are on HDFS. So far, so good? Right? I have yet to give you the details of what there is in these HFiles, but at that point, we just store it in one or more HFiles on HDFS. By the way, since these HFiles are on HDFS, they will be made of 128 megabyte blocks, and these blocks are going to be replicated over at least three machines by default, right? These are just 0815 HDFS files, right? Okay, 0815 is just a German expression to say quite standard, right? As we've seen them 2 weeks ago. All right. Now let's zoom in. Let's continue to zoom in to see what there is in an HFile. In fact, this I've already told you a few minutes ago when somebody asked about the column-oriented storage, and I told you, be careful, it's not a column-oriented storage, it's a wide column store, so it's column family-oriented. And so I already told you that the order in which we are going to store all of these values, that's a store, that's a logical table, that's a region, and that's a single column family, is this, then this, then this, then this, then this, and then this, right? Like a jigsaw, right? So this is in this order, row by row, and within one row, column by column. Okay? For whom is that clear? Right? We have a question over there. Maybe we can... Within this, these are individual values together with their coordinates. because if I just tell you the value is 42, you don't know where it comes from. I also need to say it's the ultimate answer to the question of life, the universe, and everything. So it means that when I'm saying I store the red value, I store it together with A1, right? So I'm saying A1 is the red value. So I'm saying A1, red value. The blue one would be A2, the purple one would be B1, the yellow one would be B2, the black one would be C1, and the green one would be C2. You can even see C1, C2, and B2. The others are just a bit hidden. So it's like Battleship, right? You have the coordinates of every value, and what you store is the values in this order, row by row and then column by column, together with their coordinates within the store. Do you see the key value model? Again, that it's again a key value model. A1 is the key, and red is the value. We have another question. Did I answer your question first? Yes? Okay, then?
So those tables are really sparse. So how do you, like, for example, if B2 in our table is empty, do you still have it on the HFile or not?
No, then you don't have it. So an empty cell is just not stored at all. There's not even a null, nothing. It's just not stored. There's one exception, right? It's like in French grammar. There is one exception where you might still store it, is when it was deleted, that it used to exist, but then you deleted it, then you still need to have something that tells you that, that it was deleted. But if you never stored anything there, then it's just not stored at all, right? Not even a null, right? Did I answer your question?
Yeah.
Yeah, all right. Any other raise hands? Yes, over there? On the right? We try, so the people on Zoom hear you. We try to, yeah. Maybe small hops. Yeah, go ahead.
So on page 50, no, on page 49, you said the store is like region and column family, so the intersection of those. And then on page 50, you say the store is equal to column family. Does that mean anything? Like, or?
Oh, you mean the title?
Yes, because I'm confused, like, so one store corresponds to the H file, or does the cell?
No, it's just a very bad title.
Okay.
I have to change that title. I can't even remember how did that title actually arrived here. Because no, a story is really a region plus a column family in there. Yeah, so thank you for spotting that. Did you have a question beyond that, or?
No, so you could say that a store corresponds to one H file.
A store might correspond to 1 or 2 or 3 or more HFiles. And I will show you why. Exactly, it can be more than one, right? I'll explain to you exactly why. I just haven't done that yet, but I will explain why it can be more than one HFile. At first, it's going to be one HFile, but then it can be more.
Okay,
right?
thank you.
I'll explain everything. Yeah, and we still have time. Any questions? More questions? Not in the lecture hall on Zoom? I see you too on Zoom, right? So no, there's no questions on Zoom. Yeah. Okay. All right, and I'll fix that horrible title that is just missed. This is the right one. It's a region and column family. Okay. And this I have explained. It's a key value model where we have as the key the coordinates within that two-dimensional grid, like A1, A2, and so on. And of course, you know that A is actually a sequence of bytes and 1 is a sequence of bytes, right? But just to simplify the slides. Okay, and all of that can be stored in an H file. And as we'll see later, more than one. So then what do you learn here? An H file is just a sequence of key values where the key is the row ID column coordinates and the value is what you have in the cell. Who is with me? Right, okay. And I have one more thing to add. It's that we have a cool feature that I didn't mention before, is that HBase is able to version. It means that it can keep track if you change the value in a column, it's able to keep track of the versions. Although by default, it keeps track of one version. So by default, it's not going to retain older ones, but you can ask it, please keep track of the last 5 versions, for example. It's absolutely able to do that. So if you ask it to keep more than 1 version, then it's going to create a different version every time, version 1, version 2, version 3, version 4, and then it's going to store them also in I think it's the decreasing order, if I correctly remember. So first the last version, and then all the way decreasing. So you might have several competing values for A1. It's just different versions over time, right? Okay. So these are the versions. Now you saw that because we have versions that have numbers, then it means we have strong consistency, right? You remember, if we have a linear versioning system, that's a total order, and we have strong consistency. If we had eventual consistency, we would have a DAG, exactly, a DAG of versions, the vector clocks. But here we don't have any vector clocks, it's just linear, right? Makes things a bit simple. So it's just linear, but the cost of that, the cost of this linearity is that we need to have a lock. Whenever you modify something, you have a lock on the row and nobody else can modify it at the same time, right? It means we don't have these, all of this logic of vector clocks and eventual consistency and the branching and so on. We don't have that in HBase. It's all linear and there is an increase in the versions, right? Okay. So now I keep zooming in until everybody gets scared and I have to stop for today. So if we zoom in, we continue to zoom in. So at that point, if we continue, thank you. If we continue to zoom in, we'll see that when I store these key values, this is still not something physical, because the only thing physical on a disk is bytes, right? That's the only thing that a disk can store is bytes. So this is still not physical enough. So we need to actually make them bytes. So we are going to turn these 2 bytes, these 2 bytes, these 2 bytes, and just in the order in which the key values appear, we store a key value, a key value, a key value, a key value. So this is what you have on the actual file on HDFS. It's going to be just a sequence of key values like that. It has extra structure. Of course, it's a bit more complex than that. There's other metadata parts and so on, but on the very high level, it's just a sequence of key values that we store in an H file. Are you scared yet? Can I continue? So we have these key values. Now let's zoom in all the way into one key value. So what do we store in the key value? Well, we store the key and we store the value. That part should be simple. But here is something more. We also store, before the key and the value, the length of the key, how many bytes it has, and the length of the value, how many bytes it has. Why do we need to do this? Because when I read that from the disk, all I see are bytes. So how do I know what the boundaries are of the key values? I just see bytes. I don't know where they start and where they stop. So I need to have a way of knowing when they start and where they stop. And for this, we have something beautiful called a prefix code. Who knows what a prefix code is? Okay. Who has ever used a phone? Who has ever used, wait, a landline phone? Okay, many of you. Have you ever wondered, when you have a landline phone, you start dialing and you're not done yet with the whole phone number and nothing happens, it's just blank. And the moment you press the last digit, it just dials. Have you ever wondered how that is? How does it know that the phone number has ended, right? Because it does need to be 10 digits. If you call an international number, or even within ETH, it's 5 numbers. But if you call an outside number with a 0, then it's more. So who has ever wondered how it knows that the phone number ends, right? It has a name. It's because the phone numbering system is a prefix code. And a prefix code means that you cannot have 2 phone numbers such that one is the prefix of another. There is no ambiguity, so you always know when it ends. So we have here an example who was in information retrieval, right? So you see, surprise, surprise, the gamma code is back, but just as an example, if you've never seen the gamma code, you don't need to worry too much about it. the gamma code is just a beautiful encoding system that turns out that happens to be a prefix code. So it means that when you see a sequence like that, just zeros and ones, you don't know what starts where and what stops where, right? But the gamma code is magic. Don't worry, you don't need to know the details. All you need to know is that you count the number of ones until you reach a 0, and the number of ones you see here tells you how many bits you read after that. So here it's only 1, 1. So you just read one more bit. That gives you, so you take that bit and add a 0, that gives you the number in base 2. So that's decoded as 2. 1, 0 is 2, right? Then the next one, how many ones? 1, 2, 3, 4, 5, 6, 7, 8 nines. So you just, then the 0, then you count. So the first 0 you see tells you it stops, right? Then you just consume 8 more because there were 8 ones here. So you consume 8 more here and you stop here. Put all of your bits here and add a leading one. And then you can decode that to a number. I'm not smart enough to do it directly, but this is some number. Then you have 1, 1, 0, so there's 2 ones, so you decode 2 more bits, and then you have 3 of them, so you decode 3 more, and so on. Do you see the magic? Even though we didn't have any boundaries, we managed to dynamically reproduce the boundaries with the numbers of ones. Who sees that? Right? That's called the prefix codes. That's the sort of thing that you do. So in other words, we encoded the length as this here. It's an encoding of the number of bits to read. Do you remember what it's called, this encoding? Unary encoding. And what is the fancy name for it, the cool name for the unary encoding? I think I heard it. Not red sum? Oh, red Solomon. Oh, that one I actually don't know. I heard of it, but I don't know the details of that one. No, I had an everyday object name in mind. Yes? Yes, the thermometer encoding. It's like a thermometer, right? It just grows with more ones if you add more. So that's the thermometer encoding. Okay, very good. All right, that was for those of you who visited information retrieval so that you make some connections. But you don't need to worry too much if you didn't, because all you need to know is that if I just go back here, we don't use a thermometer encoding here. We do something much simpler than a thermometer encoding. I just here have 4 bytes. It's a 32-bit integer, always 4 bytes. That tells me the length of the key, and then I know how much to read. Then I have the value length, always 4 bytes, and then I know how much to read. So it means that if I go from left to right, now I know the length of the key. Now I know the length of the value. So I read that many bits for the key and that many bits for the value, and then I know exactly where it stops. Then I read the next key value. Who is with me? Right? Awesome. Just thinking I should let you go at that point, I think. Then we'll continue to zoom in even more tomorrow, but I think that's enough for today. So thank you very much, everybody, and I'll see you tomorrow at 9 a.m.